Hello, everybody. Welcome back. Today, I'm going to talk about some things that I find very interesting, um, having to do with the kind of divergences that you encounter because of low energies and low momenta, rather than the ultraviolet divergences that come from high energies and high momenta. This is very intimately related to how we connect these quantum field theory calculations back to physically observable quantities. So I'm going to talk about inclusive processes again. And what we're going to talk about today is going to involve a combination of many things that we've talked about both this semester and last semester. Before I really get into things, I want to go back and provide some guidance on using the LSZ reduction formulas. So you recall what the LSZ reduction formalism told us to do. And there's a long derivation, but we got a prescription in the end, basically a recipe for how to take Feynman diagrams and connect them to physical cross sections. Okay, we said that we look at all the external legs and we want those to correspond to the asymptotically distant in both space and time states that we would measure, say, in an experiment. And the prescription was to replace each of the external legs by, well, to truncate it, so treat it as if it's just the lowest order propagator, but multiply each of those external legs by the square root of the residue of the interacting propagator. That's the prescription, but it's a little bit abstract at this point. Here it is again. Truncate the amplitudes and multiply by square root of the residue. And I want to show you how to go about doing that in a little bit more detail for practical situations. So I'm going to start by considering one of the simplest theories that we can use to illustrate things. That's the phi cube theory, the ordinary phi cube theory that has a divergence at lowest order. It could be in 4 dimensions or 6 dimensions. And I'm going to notate the propagator this way. This is a full propagator. Okay, so we've got the external lines of the propagator, but then this particle propagating along can interact with itself in a million different ways. We just start adding diagrams. And the full propagator is going to look something like this. There's going to be a pole at p squared equal to m squared. Okay, the pole mass, we would call it. And then in the numerator, up to a factor of I, there is a residue at p squared equal to m squared, and that's what we want to figure out. And then the LSZ reduction formalism says replace all these external particles by just the square root of the residue. Okay. So how to do this in practice? That's the question for today, at least for right now. Okay, so let's go through the steps for this phi cube theory, this simple scalar theory. And what I want to do is start by taking that propagator, that general propagator, and let's imagine writing it in a perturbation theory expansion, the way we would normally do it. Okay, we've got the 0th order, and then we can start adding loops, and we still have, say, the external propagators here. Okay, you could just write down the Feynman diagram expression for this. And we also have to account for the counter terms that the renormalization program tells us we have to include. Okay, and then of course you can have higher and higher orders. And what I want to do is first express it in this way. So let's write it as I over p squared minus m squared, the pole mass squared, and then a minus capital M squared. That is some function of p squared. And we'll say, let's let this term down here in the denominator contain all of the p squared dependent effects from all these higher order diagrams. Okay, so let's ask what effect that has. Well, first of all, if p squared equal to little m squared is the pole, okay, then m squared of p squared has to vanish at p squared equal to m squared. And so if we expand that capital M squared excuse me, in powers, if we expand it around p squared equal to m squared, in a Taylor series, we get something like this. Okay, so the lowest order term has to be 0. Okay, and then I note that I can write this line as I can factor out a p squared minus n squared in the denominator and write the denominator this way. And then when p squared is, well, if m squared is something I'm expanding in perturbation theory, then I can take this factor, I can expand it, and it goes into the numerator when I expand in the Taylor series, but with the minus sign coming at plus sign. And I can expand out to higher and higher orders. And you see a pattern coming out. You see something that just looks like the lowest order diagram. And then you see external legs, I over p squared minus m squared. That kind of looks like this diagram. And then something squeezed in the middle. And I can keep writing all the higher order terms. Okay, now keep that in your mind. So let's put a pin in this expression and think of another way that I could write things. I'm going to start by saying, let's define this object that we call the one particle irreducible diagrams. Okay. And let me zoom up here. What you see in here is 1pi, that stands for one particle irreducible. This is a definition. So you see I put the 3 lines here to say this is a definition. And what I'm going to do is draw all the diagrams. I'm not going to include the external legs here on these particular diagrams, but I'm going to include all the diagrams that cannot be reduced to a single particle going through the middle by cutting in some way. Okay, so something that is not a one particle irreducible diagram would be something like this. Right, because I can take this diagram here and I can slice right here. And you see that in the middle, there's basically a one particle diagram, something propagating that's just one particle. Okay, so that is not part of the one particle irreducible diagrams. Okay, again, I have to make sure to keep track of the counterterm diagrams here. And the reason I do that is because I can also note that I can write that general propagator in terms of these one particle irreducible diagrams. Okay, so this is just what I wrote previously, a few slides earlier, a few pages earlier, so back here. And I'm noting that I can also write it as the lowest order diagram plus lowest order diagrams with the 1pi graph in between. And then I can write it as something with 3 of the one particle propagators with 2 1pi graphs in between, plus ... so forth. Graphs with 3 1pi diagrams in between and so forth. And that's just another way of expressing this expansion. And the reason that I'm doing that is because, well, here's the actual expression that I get if I do that. So 1pi here means these graphs, or this sum of graphs. And the reason I'm doing that is because now I can compare back to what I wrote back here and see that those 1pi diagrams are just minus I times what I had in this denominator up here. So I know now what m squared of p squared is. It's I times the sum of 1pi diagrams, 1pi graphs, single particle irreducible graphs. So in other words, the m squared is I times the 1pi graphs. And remember, there are no external propagators here in these kind of graphs. I just draw those lines sticking out at the ends to remind you that this is part of a self-energy diagram. But in practice, you would not write I over p squared minus m squared for those external lines in this particular expression. Okay, so that's just a setup. We know now what m squared of p squared is, and we know how to calculate it. We calculate it by starting to write down 1pi diagrams. Now here is again, the full propagator written in terms of that capital M squared. And remember how we said that the m squared of p squared gets expanded. Let me write it in just one more way. Let's look at the region of p squared close to m squared, close to the pole, so that I can use this expansion. And if I use this expansion, then I can write that denominator in this way. And again, I'm thinking m squared close to p squared. And now I can identify the residue. If I'm doing an expansion in small coupling, so the m squared is a function of the coupling, then that goes into the numerator this way. Basically, the minus sign down in the denominator becomes a plus sign, and everything goes into the numerator. And I can see that this is the residue. So as expected, if I neglected all higher orders, then there would be no m squared. So this wouldn't be there, and I just have a residue of 1. So just like the free particle propagator. So we've got a prescription now. We know how to calculate the capital M squared. Now all we have to do is take the derivative with respect to p squared and put p squared equal to m squared. Okay. So how would we do that? And I would suggest that you try doing this as an exercise. Square root of residue would be square root of 1 plus this derivative with p squared equal to m squared. If we expand that square root, then we just get a 1/2 in front of the derivative. And you could imagine calculating it to order lambda squared if we're in lambda phi cube theory. Then there would be order lambda the 4th corrections that we might neglect. And what would you calculate diagrammatically? Well, you'd have 1 plus, and then the m squared is I times the 1 particle irreducible graphs. Okay, and the order lambda squared 1 particle irreducible graph would be something like this. It would just be a loop. It would diverge, so you would want to include the counter term, the 1 over epsilon if you're doing minimal subtraction. Then you would take the derivative with respect to p squared, okay, and set p squared equal to 0. Or excuse me, set p squared equal to m squared. And then the 1/2 is from the 1/2 from expanding that square root. Okay, so I'm not going to go through that calculation, but you could do that now, right? And then you would have the square root of the residue. And if you're calculating a scattering cross-section of phi cube theory, you would just multiply the truncated diagrams would come with each external leg multiplied by that square root of the residue. So that was for phi cube theory. And we often work with theories with different spins. So for example, a theory with a Dirac spinner or fermion, okay, would be something like the Yukawa theory. And we'll use that here in a second for some more illustration examples. The steps are more or less the same. Okay, so the propagator looks like this now, almost the same as in the scalar theory, but now we have p slash minus m in the denominator rather than p squared minus m squared. And remember that this notation basically just means p slash plus m over p squared minus m squared. So it's the inverse of p slash minus m, right? If I expand all that out, then I get 1. Okay, so from here forward, I'm copying and pasting all the previous slides that I used for the phi cube theory, and I'm just putting a red prime on the 2 to remind you that this is just a copy and pasted version of the previous phi cube theory pages of my notes, and I'm making the modifications necessary to make this for fermions. So I'm putting arrows on these lines to indicate that now we have a propagator for a fermion going along, and I'm putting dots for the loop because it's a scalar now that's interacting with the fermion. Everything else is more or less the same, except the propagator here looks like the previous propagator for the scalar theory, but now it's p slash minus m in the denominator, and it's minus just a single m as a function of p slash now. But essentially the situation is the same. The p of m, the m of p slash can be expanded. Okay, if p slash equals to m is the pole, then we expand capital M in this way. Now, to understand these kind of derivatives, just note that p slash times p slash, is equal to p squared, and p slash equal to m. What we mean by that is actually p slash equal to m times a unit operator in Dirac indices, and then there should be a unit operator in Dirac indices up here. If you take into account identities like this, then you should be able to convince yourself that derivatives like this can be manipulated as if it's just an ordinary derivative, even though you're differentiating with respect to something with Dirac indices. Okay, just treat the p slash like something you can differentiate in an ordinary way. Okay, and you can do this expansion. Now the steps going forward are more or less the same as the phi cube theory again. So again, copying the previous slides, we can take the general full propagator, pull out a factor of p slash minus m in the denominator, and we get this type of expression, which if we do an expansion, a Taylor expansion, and put that up in the numerator, looks like this. Which if we expand out, looks like this. So you should see where things are going now. We're setting up something that we can express in terms of 1pi, single particle irreducible diagrams again. And now it's going to be the minus I m of p slash that we look at. Okay. So namely, the 1pi diagrams look like this. And remember, when I draw this 1pi notation, I'm not including the external propagator lines here. So we have a diagram like this. We have to draw all the diagrams that are one particle irreducible. We can't cut through the middle and only cut a single line. Okay, so that would include diagrams like this, all higher orders. Don't forget the counterterm diagram. And then, of course, we can take the original way that we expanded the propagator to all orders and express that in terms of a sum of 1pi diagrams. So propagator, then two propagators with a 1pi diagram sandwiched in between, then three propagators with 1pi diagrams sandwiched in between, and so forth. That just looks like this. And then going back here, a few pages earlier, and comparing with this expression, we see that that 1pi diagram is just this thing right here. So we know that m of p slash is I times the sum of all one particle irreducible graphs. Right here. Okay, still just repeating what we did for the scalar theory. I'm going to take the full fermion propagator here. I'm going to remember how I expanded m of p slash around the pole, so around p slash equal to m. And I'm going to look at p slash close to m and do that expansion. Okay, so if I use this expansion up in here, then I get this in the denominator of the propagator. And if I expand again so that I can move this factor into the numerator, then the minus sign becomes a plus sign. And here we have the residue. So the residue is 1 plus this derivative with p slash equal to m. And we know that the capital M, what I call the capital M up here, is just I times the sum of single particle irreducible graphs. And again, finally, we can do the lowest order calculation. let's call the coupling in the Yukawa theory G, going here forward, the coupling between the scalar and the fermion. We'll call that that coupling G. And if I expand the square root, I get 1, the 1/2 from the square root, this derivative, and I'm imagining that I'm going to calculate just the lowest order graph, so order G squared. That's what I get from a single loop. And then I will be truncating powers of G to the 4th. And what does the graph look like? We've got the I, because M is I times the one particle irreducible graphs. I get the 1/2 from here. I get this derivative with respect to T slash. Okay, I'm going to remind you here that we're not going to include external propagator lines in this type of calculation. Okay, and this is a loop graph that you should be able to calculate and get the 1/epsilon poles. And this is basically part of one of your homeworks. And you've got the counter term here to remove the 1/epsilon. Remove the 1/epsilon if you're doing minimal subtraction. So I think it would be good for you to do that calculation as an exercise. I'm not going to go through every single step because we've done several of those calculations already. You know the basic outline of that kind of calculation. If we're using standard methods, we'd probably go to 4 minus 2 epsilon dimensions to dimensionally regulate the ultraviolet divergence. Remember, this is an ultraviolet divergent graph. So we deal with that using renormalization. Okay. We know how to renormalize. And if you just assemble the pieces of the Feynman rules, you should get something like this. So we've got the I, because it's I times the sum of one particle irreducible graphs. This is the only 1pi graph at order G squared. And then you've got the integral over the loop momentum. You've got a k slash plus m for the numerator. You've got the denominator factors. Note the different masses. I have an mq squared. I'm thinking of this as being sort of like a Yukawa theory version of a quark, because I'm used to working with quarks. And ms is the mass of the scalar right here. Okay. And everything is in 4 minus 2 epsilon dimensions. I've got the mu from dimensional regularization, the mass unit that I need to make all the units consistent. Okay. I've got I times I from the vertex factors. And I've got I times I from the numerators of the propagators. So that's I to the 4th, which is 1. Okay. And then you've got a set of steps that you should be able to follow by now to convert that into something with a Feynman parameter. So generally what you'll do is you'll combine these two denominators using the Feynman prescription, where you essentially introduce another integration over a common parameter. That is what this integral here is, this integral over x. And then you basically have somewhere a table of integrals that you can just reuse over and over again. And one of them is for these kind of integrals after you do the Feynman parameterization that allows you to write this result in this way. Okay, number of steps in between that you need to fill in, but I will let you do that on your own. Okay, now you notice that I've multiplied and divided by gamma 1 minus epsilon. That's in preparation for subtracting the pole that comes with an S sub epsilon. If you look back at how we did modified minimal subtraction, that's what I want to do here from ms bar. That means that I subtract poles of the form S sub epsilon over epsilon, and S sub epsilon involves a 1 over gamma 1 minus epsilon. So I'm just getting ready to do that subtraction by including a 1 over gamma 1 minus epsilon explicitly. Okay, and then once I get this, I can differentiate. Okay, I can differentiate with respect to p slash, and I need the 1/2 from back here. Differentiate with respect to p slash and set p slash equal to m q. And again, I'm going to leave this as an exercise for you. You do it yourself. Take that derivative. You should be able to see exactly how that works. You can sort of see it already. If I take the derivative with respect to this p slash, okay, I just get x times all of this stuff. And you see that part of the result here. Then I have to account for the fact that there's a p squared down here. That's p slash times p slash. And that basically gives me this factor over here. Okay, now at the end of the day, I need to expand in small epsilon. I've got a gamma of epsilon, so that's going to give me the 1 over epsilon pole that corresponds to an ultraviolet divergence. But I know what I need to do. I need to subtract the counter term. I need to deal with this graph. So that's just going to be basically the S sub epsilon over epsilon that I need to subtract in order to get a finite answer. So if I include that, if I expand in small epsilon, identify the 1 over epsilon pole, subtract it to account for that, or subtract the S over epsilon pole to account for the counterterm graph, then I get a finite answer. That's what the renormalization program gives us. Okay, so again, I'm going to let you fill in the steps. Be a good idea for you to do that. But what you should do is find that you reproduce this expression. Okay, now you get something that is totally finite. Okay, in principle, I could do the integral over this Feynman parameter x from 0 to 1 and get an expression. I'm not going to do that, but you could do that if you wanted to. What I want to do is look at its properties. So maybe actually pause the video here. Make sure that you understand how I got to this expression for the Yukawa theory. Note the presence of the mu squared. It's still there from doing renormalization. The m's are the masses in the theory. And what they basically do is they limit the possibility for radiation at scales much lower than their values. So if you think about a Yukawa theory is a finite range force. If you think about the traditional development of the Yukawa theory, why we had it in the first place, in the 1930s, Yukawa realized we needed a short range force. Excuse me. And if he had a scalar theory, he got a force that fell off very quickly over large distances, as long as the mass was large enough. Whereas if the mass went to 0, basically recovered a Coulomb-like potential. And when you have a Coulomb-like potential, actually scattering cross-sections are divergent, right? So what happens if we take these masses to 0? We could start by taking the mass of the scalar to 0, okay? So that would be kind of like electrodynamics if the photon were a scalar. We could imagine that we're doing electrodynamics in a universe where the photon happens to be a scalar. And then it simplifies a bit down to this expression. Okay, I've just put ms squared to 0 here, and mq squared is canceled. So I get this expression. Now I've got at least one divergence here. When I integrate over this Feynman parameter x, when I get to 1, this factor diverges logarithmically. The integral 1 over 1 minus x, when I integrate up to 1, it's going to give a logarithmic divergence. Okay, and it apparently comes from having set that mass equal to 0. So we call that actually a soft divergence. But there's actually another divergence here. If I want to start taking the mass of the quark fermion, if I want to take it to 0, it's sitting inside of this logarithm right here. Okay, so actually I can't really take it to 0 because that's going to make a divergence too. So there are actually two types of what we call infrared divergences in this calculation of the residue, which, I mean, we could have a theory where we actually want to put the masses to 0. We have theories with zero mass particles, photons, right? Or we could be in a situation where the masses of the theory might make the theory very complicated, and we don't want to have to deal with them. So we might want to go to high enough energies where we're not sensitive to them. Here we're going to remain sensitive to them, right? At this stage, you might actually also want to think about what value mu would take on in an actual calculation. Okay, if it were a asymptotically free theory, this Yukawa theory is not asymptotically free, but we do a lot of calculations in the standard model in asymptotically free theories. We'd like to choose mu to be some very large scale associated with a very high energy process. Okay. If that's the case, if mu is a very large scale and the mass is some fixed scale, then this logarithm is going to get larger and larger. Okay, so it's worthwhile really to sit and pause and think about the meaning of these various divergences. Actually, it's a little bit hard to understand them in the case of this virtual graph. We'll look at the virtual graph, meaning a graph with just a loop inside of it. We'll look at some different graphs that help us understand these divergences here in a second. In anticipation of that, let me just call the x going to 1 divergence a soft divergence and the m squared going to 0 divergence a collinear divergences. Since they involve the masses going to 0, these are infrared divergences. It's coming from the fact that we're taking into account more and more of the low energy or large distance physics. It's a mirror image of the UV divergence problem. Although the way we think about them and the way that we deal with them it's going to be quite a bit different. Okay, so I hope that the discussion I gave previously, just now, about the residue calculation, I hope that clarifies how to apply LSZ in practical situations like cross sections. Okay, we're going to actually see now an example where you can apply that in a specific example process. And actually, since this is one of the last things that we'll do this semester, I'm going to use it to try to bring in all of the different techniques that we've developed over the past 2 semesters. So I'm going to harken back to many of the things we discussed earlier. There was a lot of abstract stuff, but I'm going to show how we can bring it all together and put it in the pod and get concrete predictions for physical observables. And I'm going to use one specific physical observable to make a nice illustration. Okay, as a prelude to that, let's actually think about some of the things that we've talked about these last 2 semesters. These are going to be things that you're going to see come together in this discussion today. Okay, so going back way to the beginning, we had to talk about scattering theory in the general situation where we've got relativistic states. So we related scattering theory to the S matrix and to relativistic single particle states. So scattering theory. And cross sections. Okay, of course, we also set up basic perturbation theory with interactions. So things like the Gelman-Low formula, Wick's theorem, all of that sort of stuff that allowed us to do basic stuff with Feynman diagrams when we turned on interactions. But really when things got complicated was when we started to face divergences. So like UV divergences, ultraviolet divergences from things going to very high energy. UV divergences, which we dealt with through the whole renormalization program, the whole renormalization method, UV divergences and renormalization. That allowed us to get UV finite results. Okay, and that led to the renormalization group. Renormalization group. Which was especially useful when we confronted asymptotically free theories, because it meant that we could get increasingly accurate descriptions of the very short distance behavior, by exploiting the renormalization group. So we have asymptotic freedom. Okay, now one thing that will be very important to remind yourself of here is that bonus discussion that I gave last semester about inclusive and exclusive processes. So I made quite a big deal about the distinction between what we call inclusive and exclusive processes. Inclusive versus exclusive processes. This is something you might want to pause the recording and go back and look at, because conceptually it'll be very important here. So back then I basically described the different definitions of these different types of processes. But here we'll see that it becomes very important that we establish exactly what level of exclusivity or inclusivity we're talking about, okay, when we deal with infrared type behavior, so the low energy type of stuff. And actually, this is also a place where the interaction between the theory side and the experimental side starts to become very important, because we need to make sure that we're talking about a process that we really can describe in the ways that we think we can describe it. So we'll see how that comes into play. Maybe I could also remind you that we talked about Mathematica, or more generally, computational techniques. So I won't do any calculations here that are extremely computationally challenging, but you'll see some examples of how, as things progress, as you start to add more diagrams and so forth, having a computational method to get them very quickly will be a very useful thing to have. So again, you might actually pause the recording and go back through all of these things, maybe even rewatch some of the earlier recordings to remind yourself of the concepts, because we're going to bring them all together now and see how we can do good scientific theoretical calculations using quantum field theory by putting them all together. Okay, now before we really get into the calculation that I'm going to do, which is again going to use our favorite example theory, the Yukawa theory, let me motivate it by some physical processes that people actually look at in particle physics. So what I have in mind specifically is the annihilation of a lepton in an anti-lepton pair, so E plus E minus, for example, positron electron annihilation at very high energies. So if you're in the center of mass, they annihilate and produce a virtual photon that is very off shell, but with zero momentum, but then disintegrates into a bunch of hadrons, strong interacting particles. And what you generally see in physics is collimated sprays of particles going out in different directions. And this is what I'm referring to as jets. So you might say, let's look at a jet that contains a particular type of hadron H, and then a jet generally going in the opposite direction to preserve momentum with the antiparticle H bar. So this is basically defining the process that we're going to talk about. We're going to say it's inclusive to a certain degree because we're going to sum over everything that can happen inside of each of these collimated sprays of particles. Okay, now if you were calculating this and you just started writing down Feynman diagrams, the very lowest order thing you might draw for the amplitude would be something like this. So here we've got the positron and the electron coming in, annihilating and producing this highly off-shell virtual photon. And then at lowest order in the QCD coupling, alpha S, that photon would just splinter into a quark and an anti-lepton quark pair, and they'd be going out at very high energies back to back relative to each other, because this photon here is going to have a very high energy. Okay, and in fact, if we're in the center of mass, then that photon just has a 0th component. So P0 would just be the center of mass energy of the system. Okay, and all of that energy is going to get transferred to this quark and anti-quark pair going out in opposite directions. Now, you know that in real life, you never observe a quark in an actual experiment. And when we think about asymptotic freedom, we can understand what happens. What happens is that as these quarks propagate over large distances, the large distances are involved, that means that the asymptotic freedom no longer applies, because you're talking about the dynamics over large time and distance scales. The quarks can start radiating like crazy. Lots of gluons and quark antiquark pairs come spraying out along with this particle. And so schematically, what you might start trying to draw are graphs like this, where I've drawn gluons getting spit out everywhere. And as you look at larger and larger distance scales, you have to include, essentially infinitely many of these. And as they go out, their interactions between them get so large that they just start to form basically bound state hadrons. Okay. Now, they tend to come out in the direction of the initial back-to-back quark and anti-quark. So what you actually see in an experiment is like a spray of final state hadrons. So we could imagine that the H is a pi plus and the H bar is a pi minus up here. So we can look at cross-section for producing, these sprays of particles. And I put an eyeball to indicate an observer looking at, say, at least one pi plus and at least one pi minus inside these cones of particles spraying out in the final state. Okay, so this is something that is actually observed, and it's something that people study in real experiments. So here's a famous example from 1979. This kind of cross-section is one of the things that helped establish QCD as an accepted theory of the fundamental theory of the strong interaction. And here at the top, I've drawn a theorist schematic vision of what this type of experiment looks like. So we have like a cylindrically shaped detector that's got things like calorimeters, tracking chambers, all that sort of stuff that experimentalists deal with. And an electron enters in from one side, a positron enters from the other side. If we're in the center of mass, then they'll collide somewhere in the middle of this cylinder. And if we look, say, directly down the beam pipe here, then we see the jets that are a result of the collision spraying out sort of in this way, in what I've sketched here. So what this diagram shows is the cross-section here of this detector, and you see, say, calorimeters lighting up, showing where the spray of particles is going, where these jets are going, and you can see things that track the paths of these particles. And so you actually see this sprays of very collimated groups of particles. This is actually 3 jets, not the 2 that I talked about before, but anyway, those are jets. This is what I mean by a jet, by the way. We're going to gradually get more precise about what we mean by a jet in the context of this discussion. But let me just say that you have jets in most of these theories, and these things like gauge theories. So even like in QED, if you've got an electron, if you scatter electrons and positrons and such, the electron isn't just going out by itself. You have to account for the fact that it'll generally have a cloud of nearly 0 photons all swirling around it, right? In fact, electron in electromagnetism, you know that total cross-sections are infinite because the electromagnetic force is an infinite range force. You basically have to specify a resolution scale to give a good definition for a cross-section. And that's just basically saying that charged particles carry basically a cloud, an infinitely large cloud of nearly zero energy photons. Okay, so the cloud would basically correspond to the jet in the QED case. In QCD, it's actually a literal spray of particles. Okay, now, these are both gauge theories, and calculations can spiral into complexity, into extreme complexity. And what I want to do, though, is distill the basic issues of infrared behavior without some of these complexities that we have to deal with. So I want to get to the conceptual essence of infrared behavior. And to do that, I'm going to look at a process very similar to the one that I've just used to motivate our discussion, annihilation of two particles and going into jets. But I'm going to use again, our favorite theory, the Yukawa theory. And instead of having an E plus E minus annihilate, I'm going to say, let's have two scalars annihilate and produce what we observe in the outgoing state, two jets characterized by the fact that each one has one of the fermions in it. So a Ka and a Kb. So this is the diagram that we'd be looking at lowest order in perturbation theory, the lowest non-vanishing, non-trivial order. It looks something like this, right? Have the two scalars coming in, annihilating by interacting with each other, going into a scalar that then splinters into a fermion anti-fermion pair. And I'll call these fermions quarks just to keep our analogy with the QCD example. Okay, it's Yukawa theory, so it can't really be literal quarks, but let's push the analogy and keep calling them quarks. Okay, and now we want to ask, what happens if I look at the cross-section for these particles to produce sprays of other particles going out in the final state? Okay, now, before I get really into the calculation, we need to flesh out a little bit more what we mean by sprays of particles, and basically to characterize this process a little bit more carefully. So I've drawn a diagram with planes to try to set up a good coordinate system to describe this process. What I've got are the PA and the PB coming in here. That corresponds to these incoming annihilating scalars. So this is from before the collision. And those orange particles correspond to the incoming line here, the incoming lines here on the lowest order graph. And then there is an interaction here at the interaction point in the graph that would correspond to this middle part, the hard, we'd call it the hard part here, where you've got p squared being very, very large because it's carrying all the center of mass energy. And then what I've drawn are cones, basically carving out regions of the final phase space. I'm going to say, let's look at processes where there's a quark labeled with momentum Ka going out into the final state, and an antiquark labeled with the momentum Kb going out into the final state. But we're going to include all cases where other particles can be coming along very close to the direction of Ka and Kb. And that's represented by these green dashed lines here. Okay, now what do I actually mean by these collimated cones of particles? I can specify it Lorentz invariantly if I note that the total form momentum of this outgoing line is going to be basically nearly light-like if S, the center of mass energy squared, is large. So in other words, if I label the particles that accompany Ka, these green particles, with primes, and I add all the particles in that cone together and I take the square, then if that's much less than the center of mass energy squared, then it's basically going to look like a bunch of particles going out in the same direction relative to the very different directions of these incoming particles colliding in the center of mass. So I can use that to say what I mean by a spray, a cone of particles. So all these particles together are going to act basically like an almost light-like ray relative to the overall collision. And similarly for the B particles. Okay, now to be careful, again, what do I mean by inclusive cone? What I mean is that when I do this measurement, I need to sum everything that goes into that particular kinematical region defined by the cone. That means the case of just one Ka by itself, so no green particles, that's part of the sum. The case of one green particle, the case of two green particles. So again, go back and look at what I meant when I talked about inclusive versus exclusive back here. Okay, that will be very important. Okay, so that's the process. I'm going to reiterate it here in just a second, but let me make a number of claims about what we can do with this process and what masses are basically restricting the energies of the interaction to be larger than the mass scales. Okay. So by setting masses equal to 0, we're basically allowing radiation with nearly zero energy. Okay. So we start to recover the divergent type of behavior in this example if we let the center of mass energy become infinitely large relative to these mass scales. Okay, and in fact, what I'll show with at least one sample calculation is that at least order by order in the graphs in perturbation theory, the dominant contributions are from these collimated beams when S is much larger than the mass is squared. Okay, so that actually, it makes sense then that what we see when we have these collisions is basically sprays of particles. Okay. But what I'll show is that if we make these cross-sections inclusive enough, that is, if we really appropriately sum over all the numbers and momenta of the particles inside of each of these cones, then we'll find we're able to calculate the cone cross-section, the jet cross-section, the cross-section for producing these cones of particles without any detailed knowledge of the size of these mass scales, or in other words, without any detailed knowledge of the physics of the low energy. Okay. And that actually is a very important thing to keep in mind when you think about the analogy with QCD, because in QCD, or any asymptotically free theory like QCD, what we want is to be able to use the fact that over short distances, we know how to calculate things. Okay. But over large distances, so the physics of the very large distances that is represented in this example calculation by the masses, in QCD, that stuff becomes very, very complicated, very interesting, but very horribly complicated. You need to turn to things like lattice QCD and so forth. So it would be a very nice thing, a very nice test of QCD by itself, if we could figure out how to calculate these cone cross sections using QCD, but without saying anything about that behavior over large distance scales. Okay, so far this is just an assertion. We'll see how this comes about. Along the same lines, we'll find that we can actually put the masses equal to 0 and not encounter any infrared divergences. Okay. We'll have to think about what that means physically, but basically it again says that we're not looking at the physics below a certain energy scale. All right. In QED, for example, we could say that that just corresponds to a measuring resolution. Like we don't measure effects over, we can't resolve effects below a certain energy level in QED. In QCD would mean that we're not resolving, say, the internal detailed structure of hadrons. Okay. But, and again, I'm emphasizing something I already said, This is all only going to hold if I sum and integrate over everything inside of each jet. So let me actually express that in formulas now. So what we're saying is that we're going to start with cross sections of this form. So d sigma, and it's going to be at least differential in Ka vector and Kb vector. That's the bare, or not bare, but the isolated quark and anti-quark that are coming out. And then on top of that, we can have any number of those extra green dashed particles that it can be differential in, including 0 number of green particles. We have to include that, but we could be differential in all those particles. Okay, and we have to integrate each of those momenta over a certain range if we want to say that the cross section is really inclusive. So I've got the integrals. Now to be jets, what I'm doing is I'm restricting the integrations over some phase space in the final state. And the restricted integration is represented by these deltas here. So delta A is for the range of Ka, delta B is range of Kb, and so forth. Okay, and what that symbolizes is the phase space back here in this picture corresponding to the particles having momenta inside of each of these cones. So far it's just schematic, but I'll show you how you can limit the phase space in that way. Okay, and then finally, we don't just have to integrate over everything in that range, but we also have to sum over all the numbers of different types of particles. So that's what the sum over green particles here means. That means the green particles here are these particles, these green dash particles here and down here in this other jet. We have to sum over any number and kind of those particles, including 0 of those particles. That is also part of the calculation. Okay, so again, these are the claims, and we're going to go through some steps to verify that this is really the case and see how this actually works. Okay, so what kind of graphs can contribute? Well, here again is the lowest non-vanishing order, so I'll call that LO. Okay, and then I need to start dressing it so I can have vertex diagrams. If you do this calculation, you'll actually find that it doesn't have any infrared divergences when I put the masses equal to 0 in the Okawa theory. You have external leg diagrams like this that require that you use the LSZ formalism, and we'll see an example of that. We've already set up the residue, so that should not be too difficult to push through. We've got diagrams where the outgoing scalar can split like this. Okay, and now what I'm going to do is actually restrict to a few diagrams that really illustrate the issues with the infrared behavior. Okay, I'm not going to calculate these in particular, but still I'm going to start out with this diagram, which when I do the square modulus, m squared, is going to be order gs squared g squared. Remember that g s is this coupling and g is this coupling. And then I'm going to start considering other graphs. For example, this graph has another g squared, so that would be gs squared g to the 4th. And I'm going to actually look at the non-trivial order for the A jet. Okay, so let me actually step through the cases that we're actually going to calculate. So the lowest order contribution is going to have just the quark and the anti-quark coming out basically by themselves, like this. They're trivially going to satisfy the jet condition because Ka squared and Kb squared are both mass squareds that are going to remain fixed as S gets large. And what we're saying is that we basically just need to integrate the differential cross-section differential in KBT, by the way, after we take into account all of the conservation, the energy conservation and the momentum conservation. There are really only going to be 2 components of momentum in the final state that are free to vary, right? So I'm going to use the two components kbx and kby, which together are going to be kbt. And we just need to integrate over some range that corresponds to a cone. And then we've satisfied the definition of the jet. Okay, and this is a jet with nothing but the quarks in the final state. Okay, now I'm also going to account for the case where there actually is an extra scalar emitted from the outgoing quark jet, and that's going to look something like this. Okay, so it looks almost the same as before, but now I've got a cross-section differential not just in the two components of KB, but also in the three components that Ka vector can have. So you see the quark comes out, but then it spits out one of these scalar particles, and the quark continues on its way, but it's recoiling now against one of the scalar particles. And so it has some additional Ka vector that isn't just constrained by the Kb vector. And I have to integrate over all of the Ka vector inside of a cone around the original Ka vector direction. Okay. If I call this Ka prime, actually for my calculations, I'm going to call that Kc. What I really need is Ka plus Kc squared, much less than S, to satisfy the jet condition. Okay, so I'm going to need to restrict basically the range of Ka vector. We'll see how to do that in a second. Okay, so the graphs I'm going to consider, remember there are quite a few graphs that you'd have to consider going to the next order, but I'm going to restrict to the ones that illustrate the issues with the infrared behavior. So again, we've got the lowest order, which I've written several times now. I'll call that graph A. Now, if we want to include the next order on the outgoing Ka jet, we need to have the self-energy graph. We know how to do that because we just get the residue of the propagator and use the LSC formalism. And then if I'm just looking at the effects of higher orders on this leg by itself right here, that's what I want to do today, then the only other graph to consider is one where a scalar goes out into the final state after it's been radiated from the Ka leg. Okay, so this graph, actually both of the top two graphs correspond to the first event diagram that I have over here. Okay, I can't really distinguish between the first two graphs because both just end up with one of these particles, with the quark A and the quark B in the final state. Now the third graph here, that actually corresponds to a different final state than the first two graphs. It means that there's an extra scalar particle in the final state. So I'm actually observing something different in the final state. And that corresponds in the event diagrams to this type of diagram. Okay, now one thing that's going to simplify this calculation a lot is that all of these graphs, in all of these graphs, they all involve the same triple point interaction as the initial part right here. And since it's just a simple scalar theory, the Feynman graph expression for that is rather simple. So let me just take it out and put it down here. Call that capital L, that factor. And all it is this propagator, which is I over p squared minus m scalar squared. And this vertex, which is minus I gs. And so it's simply gs over s. And I put approximately over s because in the end, I'm going to look at the limit that s is much larger than the masses squared. Okay, and remember that p squared is equal to s. because it's just the center of mass energy squared. Okay. So actually what we're going to start out looking at is the square modulus of this diagram. So this is going to go into an m squared calculation. And when I take the square modulus and sum over the final state, then the graph looks like this. So I have the original diagram, it's permission conjugate, and I might put a delta on the final state to indicate that I'm going to restrict the range of integration to correspond to a jet for the outgoing particles. Okay, so this is the diagram we have to calculate. Remember, this S means it's summing over final states, so it's kind of like an integral sign. Okay, this is what we need to calculate now. Now, before I really get into doing that, we need to do a little bit more setup. So I first want to change the coordinates to something that will be convenient. And then I also want to list a set of results, a set of basic expressions that apply in the collinear jet limit. So in the limit that this Ka and this Kc are both spraying out in almost the same direction. So first, let's look at the coordinate system. So what I'm going to do is basically rotate the coordinate system, so I might call it the R frame for rotated frame, so that the Z axis is lying right along the direction of the B particle. Okay, so that'll simplify things because that means the B particle has no transverse components in this coordinate system. Here's a diagram of what it looks like if you look head on to the collision in that coordinate system. Okay, again, you're sort of looking down the beam pipe. And here's the point of the collision. So this is right where the virtual photon splits into the quark-antiquark pair. Here goes the antiquark, here goes the quark up. It goes along for a while with the total momentum of Ka plus Kc, that's the total form momentum, which then splits into the observed momentum of the quark and the final state momentum of the scalar. Now, since the total x component or transverse component of momentum has to be 0, okay, by momentum conservation, then each of these particles carries an equal and opposite transverse component of momentum. So I'll call it Ka perp, Ka transverse, and negative Ka transverse. Okay, so now how do we characterize the collinear region? Well, really, it's ultimately going to be when these transverse components are very small, so that both of these particles are going out in the same direction. Okay, it'll be useful to have this picture in mind as we head forward. Okay, so we've actually got two constraints. We know that Ka plus Kc, quantity squared, has to be much less than the center of mass squared. And actually, let me just say that order m squared means of order any of these masses that we're going to consider to be small. So it could be order mq squared, ms squared, or some combination thereof. Okay. So we have that condition, but also Ka plus Kc is the same as Kb minus P, and that has to be order m squared. So one thing we can do is we can just expand that out. That becomes negative 2 P dot Kb, but P dot Kb is just square root of S times the 0th order of Kb, and then P squared is S, Kb squared is order m squared. So I'm just re-expressing that here. And what that tells us is that Kb0 is up to terms that go to 0, like m squared over the center of mass energy, is equal to square root of S over 2. So center of mass energy over 2, which which makes sense. Basically, we're dividing the center of mass energy between this outgoing quark, antiquark, and this outgoing pair of particles. Some other relations that we need as we go to large S large relative to actually all of these things. Now I'm going to say S is large not only relative to mq squared and ms squared, but since we're now looking at the small transverse momentum here, that's the collinear jet limit, the collimated set of particles, then KAT squared also has to be much less than the center of mass energy squared. Okay, so let's look at a few more ways that we can expand things. KB0 from the relativistic dispersion relation is equal to z component squared plus mq squared, no transverse components because of the choice of coordinate system. And if we do an expansion, then that's just saying that KB0 is basically the same as KBZ. And remember that M is any of these small scales in this accounting. Of course, we've already said that Kc is equal to the opposite of Kc transverse is opposite Ka transverse. That's what I expressed with this diagram. So this is Kat transverse. Kb vector is equal to 0. So I'm just tabulating facts about this coordinate system and about the limit of large S, okay? Now this will be important, these two relations. Okay, again, just using the relativistic dispersion relation, Ka0 is square root m squared plus the 3 vector squared. Okay, and I'm going to expand these, but for reasons that'll become clear in a second, I'm actually going to go to the second order, and I'm only going to neglect m to the 4th over s to the 3/2 powers. You'll see why I'm doing that in a second. So if I say that Kaz in the collinear limit, Kaz is also of order square root of s, so also center of mass energy squared. So that has to be the case if Ka is going out and carrying all the momentum of the jet, or a large portion of the momentum of the jet, then it has a very large energy. It has a large magnitude of its 3 vector. Then this is going to be, this first term is roughly of size square root of s. And then that means that this term is roughly of size m squared over square root of s. And then the next suppression leaves me with something like this. Okay, and then I can do a similar type of expansion for Kc0, the energy of the C particle, the scalar. Okay, again, I'm just making a list of these because I'm going to use them on the next set of notes. Now, momentum conservation tells me that Kcz is just equal to the negative of Kaz and Kbz. Okay, so that means, given that I know that Kbz is equal to square root of s over 2 plus suppressed contributions, I have this relation. Now I'm going to introduce a definition that'll be useful later. I'm going to introduce a momentum fraction. Okay, so this is a definition of x. I'm going to say let Kaz equal negative some fraction of Kbz. Okay, and one thing that allows me to do is to note that Kbz, remember, is equal to square root s over 2 plus suppressed corrections. And so that means I can write Kaz is equal to a momentum fraction I'm calling x times negative root s over 2. And then from this expression, I can likewise write that kcz is -1 minus x, 1 minus the momentum fraction, times root s over 2. So this is just a set of a combination of definitions and expansions and applications of momentum and energy conservation that'll make the next set of steps simpler. At this stage, I'm going through things a little bit more slowly because this is going to be a relatively new type of calculation, I think, for you. So the next thing that is also useful is to just list a set of the scalar products that we might encounter using the results from these expansions. So for example, I'm probably going to encounter Ka dotted into Kc, the scalar product of those two outgoing particles in the jet. Here's just the definition of the scalar product. Note that I have, instead of negative Ka t dotted into Kct, since Kct is equal to negative of Kat, that just becomes plus Kat squared. Okay, and now I'm also going to plug in my expressions from the previous slides, from the previous pages, for Ka0 and Kc0. I'm going to plug those in right here. Okay, now you see why I actually kept them to several orders in 1 over square root of s, because what happens is that Kaz and Kcz here cancel with this Kaz, Kcz, so that actually the leading power in Ka dot Kc is going to be order m squared. And this is, of course, all up to these terms that are going to 0 as square root of s gets large. Okay, so I'm just expanding out what I had up here on the previous line. Go ahead and do that. This is after I've canceled the Kaz, Kcz with this combination. Then I just have ratios of Kcz and Kaz here and here, still carrying along the Kat squared. And then I can use the expression with the momentum fractions to write these ratios, Kcz over Kaz and the inverse. And if I just plug in these expressions, so this expression, okay, and this expression, and I drop the power suppressed terms, then I can express those ratios as 1 minus x over x and x over 1 minus x. Now, we might need to think carefully about this value of x. Okay, x actually should lie between 0 and 1. Why? Because if this momentum fraction is less than 0, for example, that means that Ka is now going in the direction of Kb. Right? Then it should belong in a jet associated with Kb, if that's the case. Right? If x is equal to 1 or larger, then the same can be said about Kc. So if I want these two particles to both be going in generally the same direction, then at least the x has to lie between 0 and 1. Okay, so I'm imagining some fixed x between 0 and 1. And then if I do that and I substitute this, and this into my expressions, then I get that Ka dot Kc is equal to this. So I've just pulled out a 1 over 2 x1 minus x because of these ratios involving x. And you should start to see basically a familiar combination of terms. Now there's one more scalar product that might turn out to be useful. That's Kc dotted into P. And since P just has a 0th component, that's Kc0, P0. P0 is root s. And remember that KC0 is negative KCZ up to small corrections. And note that it's a negative sign of KCZ relative to the energy because, well, we kept track of the signs back here when we did this expansion. Remember that KAZ squared is, well, squared inside of the relativistic dispersion relation. But just by the setup of the problem, we know that that Ka is going opposite the direction of Kb, and it was Kb that we used to define the z-axis. And so we know that the KAZ has to come with a minus sign. Okay, so, and same for KCZ, and so that's what we've used here. And then remember that KCZ we said was negative 1 minus x over 2 times square root of s, so the 2 square roots of s combined. And so we get a nice simple expression up to orders m squared for Kc dot p. Okay, now go back to what we said many notes back now, way back here. Well, we said Ka plus Kc squared has to be small relative to s. Basically reiterating what we said in the picture. What we said in the picture back here, we're just applying that here. So that's our condition. And so we can basically confirm that the small transverse momentum constraint is what we need to limit ourselves to collinear configurations. So just expanding out Ka plus Kc squared, we've got masses, those are going to be fixed, so they're not going to be large. We have 2 Ka dot Kc. On the previous page, we've got the expression for Ka dot Kc. Now, if we consider a fixed region of x, okay, we consider a fixed region of x somewhere between 0 and 1, so that we're really looking at a collinear type of configuration, then what we really need to do to stay in the collimated jet type of configuration is for Kat squared to be small. And that, of course, makes perfect sense if we look at the diagram that we drew back here. These two need to be aligned with one another. Okay. And so going forward, I'm saying that very clearly here because one way that we can ensure that when we integrate, remember I put the delta A here, what we can do is say, just make this integration over transverse momentum. That will be pi Kat squared if we integrate over the azimuth. We can integrate from 0 to some cutoff, we'll say Km for max squared, that limits Kat to be small enough to be considered in the jet. And that will be what we'll use to define the jet in this example. Okay, now you might want to be thinking about this x. Okay, we basically said by fiat that we're looking at a particular range of x, but that's going to come back and we're going to have to think about that going forward. So I'm just making a comment about it here so that you have it in the back of your mind. Okay, so now we can calculate the m squared, the square modulus of the amplitude, but we ultimately want to substitute that into an expression for the cross-section, because that's the observable that we're interested in. So you can go all the way back to the beginning of last semester, look up the expression that we derived for a generic 2 to n cross-section. Now we're looking at the 2 to 3 case, and the generic expression actually for any kind of process for the 2 to 3 cross-section is something like this, just with everything labeled in accordance with our specific example. Now I'm going to want to reduce this down, I want to basically, first of all, take all the delta functions I can take to get rid of as many integrations as I can. But I also want to make some of these approximations that simplify the expression when S is much larger than the masses squared. So let's do that. So the first thing I'm going to do is, well, I want to get the cross section to be differential. Basically, I want to use KBT again to establish that basically the orientation of our axes. So I'm going to first of all eliminate the integration over KC by evaluating this delta function. So then I'm left with this. And by the way, now I'm putting a little 3 here to indicate that we're looking at the squared amplitude for the 3 final state particle situation. Just to keep in mind what we're talking about, we're ultimately trying to calculate this graph here. Okay. So that is our next step. Now, I'm going to want to use basically this delta function, this on-shell delta function, to eliminate one component of KB. And I want to use this delta function to eliminate the other component of KB. So let me actually take a few moments to simplify the argument of this delta function. So what I'm going to do is note that after I've now taken this delta function, the Kc is actually P minus Ka minus Kb, and then I've got the minus ms squared. So I'm going to write that, expand it all out, and I get something like this. And now I'm going to want to, again, start dropping small contributions, because in the end, I'm going to want to take S to be large. So I note that I can substitute my expressions for Ka0 and Kb0 here, 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 and here, and I get this line up to order m squared errors. And actually, since I'm now dropping order m squared errors, I could in principle just drop that term as well. Okay, now in the next line here, I simply group coefficients of Kaz and coefficients of Kbz, and I note that Kaz is actually negative x root s over 2 up to errors, again, as usual. And so I can simplify further down here. Okay, this is just algebra that you can check. And finally, I can reduce the argument of the delta function down to this. And so what happens is that the delta function, delta plus kc squared minus m squared, becomes 1 over 2 root s 1 minus x, and then delta function setting kbz to be whatever it is. So that means that when I integrate kbz here, I can evaluate this delta function here, and I'm only left with this phase space factor here. Okay, so I can do a number of things. I can evaluate this delta function using the Ka integration. I can evaluate this delta function using the Kb0 integration. And I can evaluate this function, this delta function, using the Kbz integration following this re-expression of the delta function. And the result is what I get here. Okay, and then one last way of simplifying is to note that Kb0, again, up to small corrections, is root s over 2. Ka0, up to small corrections, is x root s over 2. The triangle function lambda the 1/2, if I'm, again, neglecting the masses, is simply s, okay? And so that turns this 1 over 2 square root of lambda the 1/2 into just an s, right? So I've gotten rid of one component in the integration over Ka, the 0th component, and I've gotten rid of 2 of the components of Kb integration. So that starts to simplify this quite a bit. Okay, let me just do one more thing. I'm just going to bring this over to the other side of the equation. So I have a cross-section differential in the two components of KBT, and then I have left over this integration, but I'm going to go ahead and integrate over it, specifying this phase space corresponding to the jet range that I talked about before. Okay, I've made these substitutions down here. Okay, go through and make sure that I've gotten all the factors of 2 pi right. You should be able to do that. And by the way, I'm going to start putting plus PS. PS stands for power suppressed, to account for any of these kind of order somethings that are smaller in terms of powers of S relative to the leading power. So I don't have to write order every time. Just remember that that's what that means. It's suppressed by some power of S or square root of S. Okay, so this is a good expression to have. Maybe put a box around it. Now all I have to do is do the calculation of that square modulus amplitude. And just to be more specific, okay, we said that we need to integrate, well, we need to integrate from KAZ normally would go from minus infinity to plus infinity, but we need to restrict it to that range of basically 0 to 1. So we have to restrict it to negative root S over 2 to 0. Okay. That corresponds to X lying between the range of 0 and 1, and which is what we said was what was absolutely necessary to even begin to consider this to be a jet. And we need to consider the range of KAT squared restricted to be between 0 and what we called KM squared. That was the discussion that I gave back here. Okay, so all I've done is implement what I said was defining the range of integration that corresponded to the kinematical phase space of the cone of the jet. Okay, and also now going forward, I'm going to start to assemble things together. So I'm going to start labeling equations. So this we'll start labeling equations. With this one, it'll be equation 1. So we need to work out what this squared amplitude is. Let's go through that now. So if I go back to page 14, recall what that is. Here's what that was. Okay, what I'm going to do is I'm going to chop out this region right here. I basically did that. I copied and pasted that back over here. And everything else, remember, was just this L squared, remember, and that was just GS divided by S. Okay, so I don't need to worry about that right away. I can set that aside. Let me just look at this graph. And that we know how to calculate using everything that we've learned this semester. We've got, well, we can count up the i's. We've got a minus I and an I, so that's 1. We've got an I and a minus I, and that's another factor of 1. Okay, and we've got a minus I and an I, and that's another factor of 1. So we've just got a factor of 1. And then we've got 1, 2, 3, 4 factors of g, so that's g to the 4th. And now I'm going to sum over the final state spins, and that's what gives me a trace. Remember, the trace comes from the sum over spins. So this is unpolarized final states. I take it for granted that that's understood. So that means I get a K/A plus M. Okay, then I've got the coupling and a K/A plus KC slash, that's what the momentum is here. It's KA plus KC. Then I've got the momentum here is KB, that's P minus KA plus KC in parentheses. So that's what I have here. And then I've got a minus MQ because it's now going anti-quark. Okay. That comes from summing over the spins for these two outgoing legs. Then I've got another coupling, And then I've got a Ka plus Kc internal propagator again. And then I'm back to where I started. Then I've got two factors of this denominator for each of these two propagators here. Okay, so I hope everybody could assemble that set of Feynman rules to get this graph. And that's just m3 squared. And I'm labeling this as equation 2. Okay, and now all we need to do is substitute in the various expressions and approximations that we've assembled so far. So let's go ahead and do that with the denominator squared. We go back to page 17, and we recall that up to power suppressed corrections. Remember, we're taking S to be very large. Up to power suppressed corrections, we had this result. Okay, so I can just substitute that in down here at the bottom. Okay, the denominator is actually Ka plus Kc squared minus Mq squared. And so I get a 2 times Ka dot Kc. It's this that I worked out previously. So you can just substitute in what we got for Ka dot Kc to get this for the denominator. And we've got two factors of this. So 1 over the denominator factor squared is equal to this. So we basically almost are done. We just need to calculate this trace. Now, this trace is actually something you should be able to do with a bit of notebook paper. But you can also use this to exercise your Mathematica skills and just use fine calc to do it in 2 seconds. And that's what I did, and I get this expression for the numerator trace. So this is something you should check also to get some exercise. One thing I've done is I've dropped the terms that are going like ms squared, because I know that I'm eventually going to set that equal to 0. Okay, just like I did for the calculation of the residue in the Yukawa theory. I could keep those terms, but they're kind of uninteresting since I know that I'm going to take the limit of ms squared equal to 0. I'm only keeping it here because this is the sort of place where it could affect the way the infrared divergences look. Okay. And also I expanded, I dropped, again, terms that get suppressed by powers of S because I want to keep things as simple as possible. So I could do all these things exactly. I could make everything here exact, but again, I'm looking at the collinear jet configurations and the limit that the thing is really like a collinear jet configuration. Okay, and I get this expression. So all I need to do is substitute this into the numerator back here. Substitute 1 over this denominator stuff squared here, and put all the pieces together to get this expression. So I'm saying plus power suppressed terms and plus terms that are from the numerator that depend on the scalar mass. So just make sure that I've canceled out everything. There's an x here that cancels out one of the x's up here. So that's why I just have a factor of x. There are some factors of 2 and so forth. And I'm plugging back in the L squared. Remember that L was just GS over S. So L squared is GS squared over S squared. I've got a number of factors of S floating around. So for example, I've got an S right here. So I have S over S squared. Okay, so if you just do these substitutions, you make sure that you can reproduce this expression. Okay, now all that's left is to substitute that into equation 1. Equation 1 was my general expression for the 2 to 3 cross section, again up to the power suppressed corrections. Power suppressed meaning power suppressed in the limit of a collinear jet. in the limit of a collimated jet of particles, in this case, just two particles, the Ka and the Kc particle. Okay, we're getting close to the end of this part of the calculation. In order to simplify the final steps, the final few steps a little bit, what I'm going to do is separate out the treatment of the term in the numerator that has a KAT squared and the term that has an MQ squared. It'll just be convenient to do that. So on these next few notes, that's what I'm calling term 1 and term 2. So term 1 involves KAT squared. Okay, so it's just this expression substituted into equation 1, and just looking at the KAT squared term. So confirm for yourself that when I substitute this into equation 1 and I drop the MQ squared term, take out a piece of notebook paper if that's necessary, confirm that this is what I get. Okay. And if that's what you get, and if you, here is just a direct substitution, so I haven't done anything to simplify, but now if you get rid of as many factors of S and combine as many factors as possible, you should be able to simplify that even further down to this expression. The only thing I didn't simplify is that when I converted this integration over KAZ into an integration over X, I get a factor of square root S over 2, so I can cancel out those square roots of S. Okay, and then simplify it down even further. Now, actually, this is an integration. That's a fairly simple integration, actually, for KAT squared. It's just a logarithm. But here's something tricky happens. Go ahead and do this yourself also. Just calculate this integral and confirm that you get this logarithm right here. Okay, now you'll get that logarithm, but only if you assume that Km squared, this maximum transverse momentum, is large relative to the masses here in the denominator. So in other words, only if you're allowed to neglect terms that fall off like m squared over Km squared. So to get units right, maybe I should put parentheses here, but hopefully you can see what I mean. So go ahead and do that. So that means that this transverse momentum that I integrate up to needs to be large relative to the masses. But remember, I also said that transverse momentum, all the transverse momentum that I consider should be small relative to center of mass energy, the square root of S. So really what I'm saying now is that, I'm considering the limit where Km can be pretty big relative to the masses. The transverse momentum can be pretty big relative to the masses because Km, the limit on the transverse momentum that I'm imposing, has to be large relative to any of the masses in the problem, ms or mq. It has to be small relative to square root of s. So the transverse momentum can actually range between values that are large relative to the masses, but still need to be restricted to be small relative to the center of mass energy. Okay. So that makes sense. As the energy gets larger, as the center of mass energy gets larger, I can allow the cone to spread out, and it's still going to be a very narrow cone relative to the overall center of mass energy. Okay. So one thing I'm going to do to make comparing with the other graphs simpler is I'm just going to change variables from x to 1 minus x, and all that does is change this coefficient inside the integrand here from 1 minus x to x, and it's going to change this factor multiplying mq squared to x squared and this x to 1 minus x, and so I get an expression like this. And then again, just like in the case of the residue that I calculated for the Euclid theory, what I really want is to consider first the limit that I put the scalar mass to 0. So again, that would be kind of like a scalar version of electrodynamics. I'm going to put ms equal to 0, and this will start to illustrate the kinds of divergences that we have to encounter. And I get this expression. Okay. Now I'm not quite done because this was only for the term with a kat squared in the numerator. If I calculate the term that has an mq squared in the numerator, that's actually just exactly the same as this graph, what I called term 1. Now I'm going to call it term 2, but instead of a kat squared, I'm going to have this mq squared 1 plus x squared, and that's what I have here. Okay, now calculation proceeds as before in more or less the same way, but the integration over kat squared is just a little bit different. Now again, I still have to assume that I can integrate, that the maximum transverse momentum that I can integrate to is much greater than the masses in the problem, just like I did back here. Still much less than square root of s. And then again, this is now a very simple integral to do. Just take out a piece of notebook paper and do it. It just gives me this expression. Again, if I neglect the m squared over k maximum squared. Okay, again, I can take ms squared to be 0. That's the limit that I'm really interested in ultimately getting at. And in that limit, this term goes away, the mq squareds cancel out, and the integral I get is just like this. Okay, so altogether, the total cross-section, I'm putting everything together now, the total cross-section is the term 1 and the term 2. This is the cross-section for the 2 to 3 type of interaction. And it has this form, and plus, I should also say plus other power suppressed terms. So I dropped power suppressed terms that vanish like a power of 1 on square root of s. And I've dropped terms that I don't care about anymore now because I'm setting ms squared equal to 0. And I'm dropping terms that vanish as long as I integrate kt to large enough values way back here. Way back here. So as long, again, as I'm making the cone, the range of particles inside that cone of spray sufficiently inclusive. Okay, so this is part of the calculation. This is the 2 to 3. We still have to do the 2 to 2, right? But I skipped over that for now. This is the 2 to 3 cross-section, and you can already see some divergences. So first of all, there's a divergence in the integration over x from 0 to 1 when x approaches 1. And what is it when x approaches 1? When x is close to 1, that's when all of the momentum going in the A jet is carried by Ka, and Kc carries no momentum whatsoever. Okay, and it's divergent when the mass ms squared was set equal to 0. So actually, this wasn't divergent when if I integrate this over x, there's no divergence, right? It's only divergent when I set ms squared equal to 0. So if I accounted for these terms, I should find a divergence that cancels out that divergence if I let ms squared not be equal to 0. So this is what we'd call a soft divergence because it's when Kc is able to carry basically 0 momentum. Okay. But even if we didn't have that divergence, that's an infrared divergence, we'd still have a divergence if I wanted to put mq squared equal to 0. Okay. So this is, if I really just wanted to calculate the cross-section for 2 to 3 and just end there, and if I wanted to take the limit of all the masses going to 0, I would be in rather big trouble because of these two types of divergences that I just introduced. Okay. So here's a summary of what I just said. Two types of divergences, when x goes to 1 and when mq squared goes to 0. Well, the x goes to 1 divergence is essentially an artifact of having put ms equal to 0. Okay, but remember what we said. Remember my claims way back when we first started. I claim that if we integrate over enough of a region, and if we include everything, then there will be no IR divergences, and I will actually lose sensitivity to any of the details pertaining to this MQ and MS, this large distance physics. So what have I been missing? Well, what I'm missing is I've in fact only included the 2 to 3 scattering. And remember what I said was that we also need to include the 2 to 2, right? We also need to include everything that contributes to this type of process. Namely, we need to go back and look at these types of graphs, the ones that basically invoke the LSZ formalism. So that's the next and final step that we're going to have to follow here. So let's go do that. We need to look at these graphs basically. And I'm only going to look at, again, the ones that affect the Ka final state, because those are the ones that we're actually going to need. So I'm going to return to 2 to 2 scattering. But remember from the LSZ reduction formalism, what I can basically do is just look at the 0th order calculation now, one with the truncated, not the 0th order calculation, but the lowest non-vanishing calculation. And the LSZ formalism tells me to truncate the external legs. So what the LSZ reduction formalism tells me to do is multiply, is calculate this graph. This is the lowest order non-vanishing graph. But then if I want to calculate the effect of the self-energies on the external lines, what I need to do is multiply by a square root of the residue for each external line. I truncate each external line, treat it as just a normal final state wave function, but multiply by a square root factor of each for each residue. Okay, I've got 2 of these graphs now. So I've got a square root of the residue corresponding to this graph and a square root corresponding to that final state. And I'm going to put those 2 together. And I just get one residue. And what I want to do is calculate it through order G squared. Okay, so we've already got the G here. And then in here, I'm going to want to include through order G squared. So then we'll have up to order G to the 4th contributions to M squared. So now we have to go back and write down an expression for the cross section for 2 to 2 scattering. I sort of glossed over that and went directly to the cross section for 2 to 3 scattering. So cross section for 2 to 2. Okay, so for diagrams like this. Okay, start again. We can go through this slowly. Go all the way back to the beginning of last semester and write down the explicit expression for a 2 to 2 cross section in general. Now I've got a lot of delta functions that get rid of a lot of these integrations. So actually, let me get rid of the momentum conserving delta function by integrating over all of Ka, all 4 components of Ka. And then I just have 2 on-shell delta functions. And I can get rid of again, two components of KB by integrating over each of these. Okay, first I'm going to get rid of KB0 and I get an expression like this. And by the way, I've already done lambda 1/2 approximately equal to S here. Okay, now I can use the fact that Ka is equal to P minus Kb to do this on-shelf delta function. And I can use the fact that in the large S limit, KB0 is up to power suppressed errors KBZ. Okay, to get that KBZ is up to power suppressed errors again, root S over 2, and KB0 is root S over 2. Both the same sign because the Z axis is again going to be along the direction of KB. And so doing that delta function pulls out a 2 square root of S down here. Just a few more steps. KB0 is again square root of S over 2. And so I get this expression. Or in other words, if I bring the phase space d2 kbt over 2 pi squared, then if I use that, then I can compare with the 2 to 3 scattering. If I bring that over to the other side of the expression for the cross section back here, then this is my expression for the 2 to 2 cross section. Okay, and again, dropping stuff that vanishes at large S, like power of 1 over S. Okay, and then I can calculate, what I need to do is calculate this graph, especially to get the lowest order, the lowest non-vanishing order, which I still haven't done. And I'm going to put a 2 to indicate that this is now amplitudes for 2 to 2 scattering. So here's what the graph looks like. I have, again, the L squared. Now this is something that is rather trivial to calculate. I get two factors of G, a G, a minus I and an I, so that just gives me a G squared. And then if I don't care about anything that's power suppressed relative to the leading power in S, then I just get a trace of Ka slash Kb slash. And that is all just equal to this. Again, using the expansions that I know how to use. When I drop power suppressed corrections, that's just 2G squared times S. So very simple result for this. Again, make sure that you can check and do this yourself. So that means that to lowest order, non-vanishing order, actually the M squared is like this, and I can plug it in here to get the lowest order cross section, the GS squared, G squared order cross section. By the way, I labeled this equation 4. So if I substitute in the expression for the amplitude into equation 4, here is the cross section. Note that it has the right units. Okay. Okay, so this is the cross section. The 2 to 2 calculation of the cross section I would get, actually the cross section for this jet process, if I only kept the lowest non-vanishing order. But of course, we want to go to the next order. We want to include the GS squared G to the 4th. But I know how to do that from the LSC formalism. And actually, I've got everything all set up. If you see at the top here, I've copied and pasted the square root of the residue that we calculated way back at the beginning. Okay, so let me remind you that way back on, I believe it was page 9, we did that calculation. Yep, way back here. We also had divergences. Okay. Now the x in this case was a Feynman parameter. In our calculation we just did for the 2 to 3, it was a momentum fraction, but okay, it's just a label of an integration variable. Okay, and then we said we needed to calculate this diagram, but with a factor for each of the external legs here of the square root of the residue. So if I want to include with this the next order in G squared, that is the graph from page 26, the loop on the external line, then we need this factor for each external line. That's basically just going to get rid of the 1/2 right here, right? Because we're going to get two factors of this for each of the two external legs that we looked at. Okay, so we just get one factor of the residue. Again, we go to page 9. And so to go beyond the lowest order and include the loops on the external legs, we can just substitute in our expression for the residue. And that is to say, just substitute this in over here, include two terms for this. So basically get rid of the factor of 1/2. And you should be able to verify for yourself that this is the expression that you get. And this is what I'll label as equation 5. Okay, so now we really see things starting to click into place. Now we have to slow down and think about what we're doing. What we want is the inclusive jet cross-section. That means we need the 2-to-2 case plus the 2-to-3 case, and integrated with transverse momentum going up to some km that is sufficiently large, larger than all the masses. Okay. So we've got the expressions now that we could substitute in here. We've got equation 5, that's just from the previous page. This is for the 2-to-2 and includes the lowest non-vanishing order, but also this term for the external leg loops. And we need the 2-to-3. That was from page 25, way back here. Okay, remember this? So we can just substitute those in now. Okay, combine various parts. So this term right here comes from just combining the logarithms. And this comes from combining the logarithms that have a mass scale squared inside of them. So what we end up with is a logarithm of the ratio of that maximum transverse momentum, Km squared, and the minimal subtraction mu squared, that basically sets a renormalization scale. And then we've got this term and this term. This term was from the 2-to-2 scattering with the external leg loops, where we use the LSE formalism. This was from the 2-to-3, right? Just go back and check these equations. We can do this one here. Remember, it comes with a minus sign. That's important. The signs here are critically important because of what's about to happen. Now we can reduce things even further by combining these two equations. Those just give us a 1 plus x. So basically, as x goes to 1, these two terms just cancel each other, which is easiest to see if you just combine those terms. Now we have a set of things that are quite easy to integrate. Notice that the expression now has no dependence at all on any of the mass scales. I can put the mass scales to 0 and I don't get any divergence. And I can integrate everything now. I've gotten rid of the 1/1 minus x divergence that comes when I integrate up to 1. So in fact, I can do the integration. So in fact, I can do this integration here. And after I do the integrations over x, which you can just check yourself, they're simple integrals, I get a fairly simple final answer, right? I just get g squared over 16 pi squared as a correction term times a logarithm of km over mu. And remember, km essentially defines what I mean by this jet, okay? And then just some factor of 1/2. Now, all of this, remember, we have to remember what kind of limits we're looking at. We're looking at the limits that km is small relative to the root s, so that we actually have collimated particles, that the transverse momentum is generally small. We're looking at km large relative to all the mass scales. We needed that in order to do the transverse momentum integrals. Okay. Otherwise, we have terms that are going like m over km. And we had, of course, square root of s, center mass energy, much larger than all the masses in the problem. So what I promised you have here, you have no infrared divergences in this jet calculation. And what is very nice is you don't even have to know anything about these large distance mass scales. Okay. So to summarize, this is the sum of graphs that we basically just calculated in this kind of jet limit. Okay, and this was the answer. Now, of course, there are a bunch of other graphs, but one thing to notice, and actually this is the beginning of a general pattern, a general trend of canceling infrared behavior. So one thing you notice about these graphs is that they're all essentially the same graph. It's just that this S, this summation or cut symbol, is at a different point. So all I've done is basically move where it crosses the middle of this square modulus graph. Okay, and that's a crucial part of that. That's why we basically get the cancellation from this set of graphs. Now, of course, there are other graphs. If we looked at the B jet, of course, we have exactly a mirror image of the problem. If we summed up all of these graphs, we would again get a cancellation of infrared behavior for the B jet. Now, if you look at graphs like these are also important, but they won't give any infrared divergences. So that's one reason why I haven't looked at them. Of course, you could calculate all of these and get a full calculation of the cross-section. But what I've done here is enough to show you the pattern of canceling infrared divergences. Okay, so my claims way back at the beginning, I think I've satisfied those claims, at least enough for you to think about. Okay. We've looked at a particular limit and found that we can get away with describing the final state without knowing really anything about these mass scales, and we can in fact put them to 0 and get a massless theory without having to worry about infrared divergences. So what is it actually that's happening? Well, actually, let's go back to the end. I've got a few questions for you to think about before you stop thinking about this stuff. This might help you understand conceptually the nature of these divergences more. So imagine that you're an experimentalist and you say, I want to understand the details of these jets. I want to understand them with high precision, right? It makes sense. That's a natural goal. You would think, I want to understand them with high precision. So I want to have them be very narrow, very collimated, very narrow collimated jets. Okay, so why don't I take that k sub m squared that basically told me the width of the jet and just made it very, very, very narrow. So narrow that it only can contain maybe 1 or 2 particles. Okay. The problem is, if I did that, remember that this expression was up to things that were suppressed by little m over km. Now, if I make km comparable to little m, okay, then I have to start to account for these kinds of terms. Now I have an expression that depends on the details of little m. Namely, it depends on the details of the infrared physics, the soft physics. So if this were something like QCD, then making the km very small would mean that I start to resolve stuff that has to do with, say, the binding and hadronization and all that stuff, that it goes beyond what I can do by calculating, by drawing Feynman diagrams. Okay, so that would be something of a problem. The other thing you might try to do is you might say, well, what I want to calculate when I'm dealing with jets, if I think of a sort of the naive conception of a jet, it's a spray of particles, right? Now, if I only had one particle in the spray of particles, you might reasonably think, well, that's not really a spray of anything. Just one particle by itself is not a spray of stuff. So if I want to characterize final states as being an actual spray of particles, why don't I exclude the case where there's only one particle in the jet? What would that amount to doing would be disposing of this graph, right? The one that has just 2 to 2 in the, just the 2 to 2 graphs. That means there's only one particle in each of the jets. I could get rid of that graph, but then my cross-section calculation now, what happens then? The cross-section calculation that I would have would just be the 2 to 3 graph. So namely, the cross-section expression would be like this. And now I have recovered, I no longer have the cancellation of the soft divergences. In order to deal with the 1 minus x, I can't really put ms equal to 0 anymore. I can't put mq equal to 0 anymore. Basically, I need to know the details. If I want to describe that kind of cross-section, I need to know the details of this infrared large distance physics. Okay, so I mean, I can always measure that kind of cross-section if I want to, but I'm no longer allowed to use this nice, simple jet cross-section calculation that we got over here, where we didn't even know, the details of what's going on deep inside of the jet, if I throw away that 2 to 2 cross-section. So if I really want to say that I'm using these theorems basically about jets, I actually need to make everything really inclusive. And I really need to follow carefully the definition of inclusive, right? Otherwise, the whole calculation changes. So what's happening is I'm averaging over all the different types of final states that I can have, okay? And what's happening is that there's kind of decoherence taking place, quantum mechanical decoherence, which makes sense if you look at the kind of graphs that give the effect, right? What I'm doing is basically looking at the same final state, but with different phases, the same kind of final state, right? In one case it's real, in one case it's virtual, but I'm sort of sampling what's happening in different phases of the final state and averaging over them. Okay, when that happens, you tend to average out basically interference effects. Note that these are interference graphs. So I'm averaging out interference effects, and I'm just getting sort of classical picture of some lump of stuff going out into the final state, which is great. But if I try to resolve with infinite precision, then I start to pick up basically coherence effects again. Okay, so this is a place where thinking about what you're going to measure experimentally really is going to be it's really going to be important to understand what the theory actually calculates if you want to interpret those experimental results. Okay, you need to know exactly what you're summing, what is inclusive, what is exclusive, if you want to use, say, the concept of a jet in the way that we've used it to get this kind of nice, easily manageable formula. Okay, so the general lesson is that we get rid of infrared divergences, and this works in the gauge theories, if we make cross-sections sufficiently inclusive. So you can see, say in Peshkin and Schroeder, there's treatment of infrared divergences in QED, where these kind of things are sort of buried in there. There's a very general treatment of this to all orders in perturbation theory in both initial and final states. This generally goes by the name Kinoshita-Lee-Nauenberg theorem, the KLN theorem. Okay, and in QCD, it's critical for preserving the lack of sensitivity to things that we can't calculate with Feynman diagrams. So yeah, so that gets into things like factorization theorems. Okay, I've got one final suggestion. You can do everything that you did here, but do it for the phi cube theory in 6 dimensions. So I've just drawn exactly the same graphs that we dealt with. All the steps will be almost the same, actually simpler, because you don't have any spinor indices in the scalar theory. But the phi cube theory in 6 dimensions is asymptotically free. Now remember, when we dealt with the phi cube theory in 6 dimensions, we talked about the asymptotic freedom, and we looked at graphs like, well, in this process, we would look at graphs like this. And this. Okay, and when we consider graphs like that in the limit that this internal propagator is very far off shell, we found that we could exploit the asymptotic freedom to give good calculations. But when we looked at graphs like this, where you had a loop on a final state leg, that was something associated with the large distance physics, with the large time and distance and low energy physics. And so the asymptotic freedom didn't really help there. But you can ask, what happens if we look at a cross-section where we include a sum over final states, over at least some range, some cone of final states, and we include real emissions like that? That's basically the kind of graphs that I'm looking at here. Well, you get exactly the same situation that we just saw with the Yukawa theory. You have a cancellation of the infrared behavior. Basically, you get sequestered from the infrared behavior. And so the final state legs no longer create the kind of problems that might mess up your ability to use asymptotic freedom. You can do this calculation. This is how E plus E minus calculations actually work in QCD. If you integrate over every final state, you can calculate those in perturbation theory. Okay, so that's all I have to say for today, and it's the last lecture for the semester. I hope this discussion really did bring in everything that we talked about the last 2 semesters and sort of made it concrete and showed how some of these formal issues really do impact how we interpret physically observable things. Okay, with that, I think I'll end today, and I will see everybody later, hopefully.